Okay, so this is lesson 3 of the Radians chapter from the Edexcel textbook. And I'm actually going to combine two units together, two sections together, and that's the arc lengths work and the areas work. Just because I don't think it warrants 2 separate videos. So let's have a look. We have got some formula that we already know when working with degrees. We should be able to find out and you did this in like year 8, year 9, the area of a sector, so the area of this, and the arc length, the section of the circumference, if our angle is theta degrees. The area is theta out of 360 times the pi r squared, the equation of a circle, the equation of an area of a circle, and the arc length is again theta out of 360 times 2 pi r. We can use those conversions, those equations, to help us work out equivalent equations when working in radians. So we're going to work in radians now. We've just said the arc length is theta out of 360 times 2 pi r. But what is 360 degrees? If we can convert the 360 degrees into how many radians that's equivalent to, then we can pop that value in radians in instead, and you'll notice something very useful happens. We know that 180 degrees is equal to pi radians, so 360 degrees is 2 pi radians. So if I just swap in, so this is our degrees equation, if I just swap in my 360 for 2 pi, then what happens? Well, what happens? Sorry, I've written a pi there, and that should say theta. Two pi r. Well, what happens is we can cancel some terms out. I can cancel the 2 pi on the top here and the 2 pi on the bottom here. So what that means is the arc length, which is often given the letter S, but you can just write arc length, that's just equal to the angle in radians times the radius of the circle. We usually put the r first. We usually say that arc length is equal to r theta if we're working in radians, which is really simple, really straightforward. You can do it in your head quite often. And the other thing is you've got rid of all your pi's, so it's able to be written in exact form really easily. We're not going to be having loads of decimals flying around. So arc length is equal to r theta when working in radians. And if you're given a question to find an arc length in radians, they're expecting you to stick in radians. Do not convert it back to degrees and use this old formula. It's going to take far too long. It is not what you're meant to do. For area, we've just said that in degrees, that's theta out of 360 times pi r squared. That's our degrees equation. But if we do the same thing again, if we convert the 360 into radians, which is 2 pi again, then we can't cancel the 2's this time, but we can cancel the pi. So we've got theta over 2 times r squared. That's usually written as a half, so the half first, then the r squared theta. So the area of a sector when working in radians is just a half r squared theta. Really simple, really straightforward. Again, we wouldn't be wanting to turn it back into radians and use the old formula. We want to be sticking with this, a half r squared theta for area and r theta for arc length. They're not in your formula booklet. You'll need to learn them. That needs to go on a flashcard and imprinted in your brains. I'm just going to, before I go on to those examples, I'm just going to go through a really, really simple example just to illustrate how easy it is to find the arc length and area of a circle if you're working in degrees. Just going to draw a sector. There we go. So got a sector. Let's say that the angle here is 1.2 radians. Okay, so I've given it you in radians, and the radius of the sector is 5 centimeters. What's the arc length? Well, the arc length equation is just r theta. So we just need to times 5 by 1.2. Which is 6 centimeters. So look how easy it is. Look how quick it is to find the arc length if we're working in radians. It's much quicker than turning it back into degrees. Area of the sector is a half r squared theta. So that's going to be a half times 5 squared times 1.2, which is going to be 25 times 0.6, which is 15 centimeters squared. So again, really, really simple to work out, really quick, and we've got nice round answers because of how I gave you the angle. So let's go on to a few more complicated examples. This is an old exam question from quite a few years ago now, but is a good example of the kind of things we'll be asked to do. We've first of all been asked to find the angle in radians. So we need to convert 46 degrees into radians. We know that pi radians is equal to 180 degrees. So 1 degree is pi over 180. So 46 degrees will be equal to 46 times pi over 180. We could leave that in exact form. That would be 23 pi over 90. But they've asked for it as a decimal. They've asked for it to 3 significant figures. So we have to follow that guidance. So that's 0.803 radians. Then it wants us to find the arc length. So notice that they're walking us through what they want us to do. They want us to use this answer to now find the arc length, which is just going to be r times theta, where theta is in radians. So that's going to be 8 for r times our 0.803. I'm going to use the full number from my calculator that's still on my calculator screen, not the rounded answer, because that could lead to a rounding error. So to 3 significant figures, that comes out at 6.42, and that's in centimeters. The area of the sector the area of the sector OAB is, we're going to use our half r squared theta equation. Again, I'm going to use my radians answer in the full form, not the rounded form, so that I don't have an error. And I'm going to do a half times 64 times 0.803. And that answer is 25.7 to 3 significant figures. So similar to the previous example that we've just done, but with a little bit of extra stuff to do before we got started. That's quite a common setup of an easy, in inverted commas, Radians question. Slightly more complicated are questions where they ask for shaded sections, so where they're looking for segments rather than full sectors. And the common thing that we need to do with these is find the area of a triangle. Now, the key to this is realizing that these triangles are always isosceles, because the two sides around the angle are both radiuses of circles, and therefore they're the same length. That makes finding the area of this triangle very straightforward. Again, they're asking us to work out the angle in radians first, because they want us to use the r theta and the half r squared theta formulae rather than having to worry about theta over 360. We've been asked for it in exact form this time. So 140 degrees is going to be equal to 140 times pi over 180. That's going to be 14 pi over 18, which cancels down to 7 pi over 9. And then for the main part of the question, we need the perimeter of the shaded segment. So it's not actually area this time, but this number is still going to be important because we need to find this length. The reason we need this length is because it contributes to the perimeter of the segment. So we've got two things to find. We need to find the length, the straight length of A to B, and we need to find the curved length, which is the arc length, A to B. So let's do the easy bit first. Let's do the green section first. And that's the arc length of the sector. So that is equal to r theta. R is 7. Theta in radians is 7 pi over 9. So I'm going to leave that in exact form. 49 pi over 9. To find the straight length, the yellow length, we're going to need to use the cosine rule. To find the third length when you've got two sides and the angle between those sides. So that's going to be, if I call that my A squared, or A, I should say, B and C, then we know that A squared is equal to B squared plus C squared minus 2 BC cos of A, and I'm going to use radians here, 7 pi over 9. I'm going to make sure my calculator is in radians, which it is because we converted it a couple of lessons ago. 7 squared plus 7 squared minus 2 times 7 times 7 times cos of 7 pi over 9. I'm going to root that answer. I got 173 point something. I'm going to root that answer, and that's going to give me the straight length, and it's coming out at 13.16. We need to then add these two lengths together to get the full perimeter. and that's coming out at 30.3. So that's an example of needing the cosine rule to help us with perimeter. The next example, another typical exam question, is down here. We're finding the area of the shaded region. Now, notice this is slightly different to the previous question. I've got an angle of 130 degrees, which I'm going to convert to radians in a minute, and then we need to subtract this sector to do part E. Seems like they've talked us through it. We've got lots of parts to this question, which is nice, to help us work out the shaded region. Let's start off by finding 130 degrees into radians. Again, with all of these questions, you can pause the video and have a go on your own first, and then see if you get the same answer as me. 130 degrees into radians is going to be 130 times pi over 180, which is 13 pi over 18. So that's what I'm going to keep using. I'm not going to use this 130. I'm going to use 13 pi over 18. It says find angle CDB. CDB is this angle here. So I'm going to call that X. We've got some numbers. We've got O to C. Let's redraw this triangle without the sector cut out first. So we've got X here. O to C is 8. C to D is 16. And this angle is 13 pi over 18. So to find out X, hopefully you can spot that we're going to need the sine rule this time. So sine X over 8 is equal to sine of 13 pi over 18 over 16. So sine X, sorry, I'm running out of, I'm going to just bring these questions out of the way. Sine X is going to equal the 8 and the 16 will cancel down to a half. So sine of 13 pi over 18 over 2, and X will equal the inverse sine of that. Making sure our calculator is in radians still. Sine of 13 pi over 18 over 2, inverse sine of that is 0.393 radians. Now I'm going to store that number into my calculator memory, just because it kind of feels like we're going to be needing these numbers later. I've stored that into memory A. If you don't know how to store numbers on a calculator, then I've got a couple of videos for a few different calculators on my YouTube channel. It is really, really worth you watching them, because storing a number in a calculator is just so valuable. It's really useful to be able to do. So have a look at those videos. Get used to storing numbers into a calculator if you don't already know how to do it, because it's ace. Right, length of O to D. That's this length here on my triangle. And for this we can use going to be the sine rule again once I fill in this angle. That angle is going to be pi, because that's the same as 180. Angles in a triangle add up to pi radians. So pi minus my 0.393 and minus my 13 pi over 18. Which is 0.479 or 480. So I've done that by doing pi minus the x value and minus the 13 pi over 18 value. The reason I've done that is because now I'm going to be able to do my known pairs again to find this missing value. Let's call that y. So if we take this down to here, then we can say that y over sine of 0.480 is equal to, and I'm going to use the ones we know for sure rather than the x in case I've made a mistake. That's a good technique to use. 16 over sine of 13 pi over 18. Before I do that, actually, I'm going to just store the 0.478 into memory B. So I've just done that now. So y is going to equal 16 over sine 13 pi over 18 times sine of 0.480. Which is 9.64. And I'm going to store that into memory C. Okay, then we're on to finding the area of the triangle. That's easy as well because we've got loads of information now. So the area of the triangle, we can do a half AB sine C. We've got all sides, all angles, so it doesn't matter which side and angle you use as long as it is two sides and the angle between. So if I'm using the 8 and the 16, I need to use the 0.48. If I'm using the 8 and the y, I need to use 13 pi over 18. And if I'm using the 16 and the y, I need to use the x. Really doesn't matter though. Let's do a half of, let's do the 8, the 16 and the 0.48. So half of 8 times 16 times sine, don't forget to use sine, of 0.480. And that was memory B, remember. So 0.5 times 8 times 16 times sine of B is 29.53. And that's going to need to go in memory D. So I've just stored that now. Right, so last part is to now find the area of the shaded region. So we've got the area of the white and the green together. We just need to take away the white section now. And one piece of information we were given right up at the top of the question was that this length here, O to A, is 3. That's really important because now we can find the area of this sector. So let's start off by finding the area of the sector. I'm going to need to do half r squared theta. R is 3, remember, so a half of 3 squared times 13 pi over 18, which I can leave in exact form. That's 13 pi over 4. I've already got the area of the triangle, so I just need to subtract this. So even though it seems like quite a strange shape, we've really easily found the area of this sector and we can just take it away. So shaded region is equal to 29.53 minus 13 pi over 4. I stored that 29.53 in my calculator, that was memory D, so I can just press Shift and D, Alpha and D, minus the 13 pi over 4. And that's giving me an answer of 19.3. That's an area, so centimetres squared, and I have rounded that to 3 significant figures. So that is some work on both arc lengths and areas, which means you are now able to work through exercise 5C and 5D. I've listed the page numbers. As I keep saying, any questions, just let me know. Leave a comment, email me, send me a message on Show My Homework. Just let me know. And I'll see you soon.